Hi guys, you're welcome to this lecture. I'm excited to have you here. Now in this lecture, we are going to look at the oxidation of methylene adjacent to a carbonyl functional group, and this will be lecture 8. And subsequently, we are going to look at oxidation of aldehyde and other carbonyl compounds like ketone respectively. Now, firstly, you need to actually know a methylene group that is adjacent to a carbonyl compound. Now, when you talk about a carbonyl compound, you mean a compound that has the CO double bond. So any compound that has CO double bond is carbonyl, which can be in the form of an aldehyde or it could be in the form of a ketone, right? So if you want to oxidize a methylene that is adjacent to a carbonyl, you use selenium dioxide, because that methylene is acidic in nature. Now, the mechanism of the reaction is not what you should actually pay cognizance to now. Just be able to identify that methylene group, and when it reacts with selenium oxide, it gives the oxidized form of it. So this is a carbonyl group, right? Now, here's the methylene adjacent to it. The methylene adjacent to it is this group here. A methylene group is mostly CH2 group. Something like this is what is called a methylene, right? So this methylene group, there's a group here, you know, this hydrogen, which is like CH2. So this group can be oxidized. Why? Because two hydrogens are removed from here and then oxygen is introduced. We say whenever hydrogens are removed and then whenever hydrogens are removed and oxygen is introduced into a reaction, such a reaction is said to be an oxidation reaction. So in this regard, this group here will be oxidized to give us a ketone, right? So the product of this reaction would be something like this. You form this arrow group and then you form, of course, you know this C, double bond O, right? And then you form this C and then here is arrow 1, here will be double bond O. So this is the product that is formed, which is a ketone, right? Now, this ketone can further be reduced to a carboxylic acid, or it can further be reduced to an alcohol or oxidized to a carboxylic acid. So if you reduce it, we are going to look at reduction reaction later. Now, some of the reducing agents that can actually reduce aldehyde and ketones are reagents like lithium aluminum hydride in dry. This ethyl ether must be dry or anhydrous. So dry ethyl ether. Now this reaction, if small water is present in this reaction, it will not take place, right? It will spoil the entire reaction. So it must be dry or it must be anhydrous. So this will break down, or it will be reduced rather. Whenever ketones are reduced, they give us secondary alcohol. So this group will be reduced to what we call something like this: CH. Here will be OH, right? And then here will be C, here will be OH, here will be H, and then here will be R. So this is an alcohol, or we can call it a diol because it has been reduced to 2OH group. So that is everything you need to know about this reaction. That selenium dioxide is capable of oxidizing the methylene group that is adjacent. When you say adjacent, it means close to a carbonyl group, right? If it oxidizes it, it gives us a carbonyl compound or a carbonyl group in that particular place that that methylene group is initially. So this place here will become C double bond O according to what we have here, right? This can be reduced because this is ketone, this is ketone. Ketones are reduced to alcohol, while alcohols are oxidized. Secondary alcohols are oxidized to ketone, while ketones are reduced to secondary alcohol, right? So that will give us the product of this reaction as this secondary alcohol from ketones. Same thing applicable to this. Now, this CH3, this is a methyl group. Now, but we can actually form a methylene group from here by saying, let me write it here, small, by saying that this should be something like this. Oh, sorry. I cannot draw benzene ring again. Anyhow, this will give us something like this. and here can be CH2 hydrogen, right? And here will be what? Double bond O. Is that okay? So in this case now, it is this one that will be oxidized. These 2 hydrogens will be removed from here. This is the methylene group. So 2 hydrogen will be removed from here, and then hydrogen is introduced. So if oxygen is introduced rather. So if 2 hydrogen is removed from here and oxygen is introduced, what do you think we are going to form? We are going to form a compound like this. This will be something like this. This will give us something like this, right? And then this will give us O, and then this will give us CH. Why? Because this hydrogen is still there. It was this one that we removed and oxygen introduced, CHO, right? Now this CHO, the way you see it here, it can be reduced further with lithium aluminium hydride. Lithium aluminium hydride is a reducing agent that it reduces aldehyde now to alcohol. So it will reduce this aldehyde to alcohol, and if it does that, this group here will be selectively reduced to give us a carboxylic acid, which is something like this. Let me erase this. So this will give us OH here because aldehyde is reduced to alcohol, and then of course we have our double bond oxygen, and this will be the product of this reaction. Sorry, we are reducing. So if we are reducing, it means we have to actually introduce more hydrogen and not removing. This carbon is still here. What I wrote there is wrong. So this will give us CH2OH because we are reducing aldehyde. If this is an aldehyde group, you reduce an aldehyde to a primary alcohol, 1 degree alcohol. So that is what I just did here. I reduced this aldehyde to a primary alcohol or a 1 degree alcohol. And that is basically the product of this reaction. It's pretty easy, right? So you should just be familiar with this oxidation. When aldehyde are oxidized, they give us carboxylic acid. Carboxylic acid are reduced, they give us aldehyde. When primary alcohols are oxidized, they give us aldehyde. When aldehyde are reduced, they give us primary alcohol. When ketones are reduced, they give us secondary alcohol. When secondary alcohols are oxidized, they give us ketones. So you should just be familiar with things like this, and everything here becomes very easy to you, right? Now, this is an aldehyde, this primary alcohol. Do you know why? This CHO and aldehyde. So if you are reducing it, it becomes CH2OH, right? Now, this primary alcohol, reason being that the carbon carrying the OH group is attached to only 1 more carbon and not 2. That is why we call it primary alcohol. Now let us look at other reactions. Now aldehyde are oxidized to carboxylic acid. I've said this before. And ketones, when treated with peracid, leads to the formation of esters. Now normally ketones are not oxidized. That's what I said. But if ketones are treated with peracid, you know what peracid are, right? Those carboxylic acid that has more than the required number of oxygen. For instance, this acetic acid, which is ROCOOH. Now, this is the peracid of acetic acid, which we call peracetic acid. Is that not so? So, the same thing is applicable here. We have an aldehyde, CHO. Now, when you treat this aldehyde with chromic acid is an oxidizing agent, or chromium trioxide is an oxidizing agent, which can be the form of sodium chromate, right? Sodium dichromate. This will be oxidized to a carboxylic acid. So whenever this aldehyde reacts with an oxidizing agent such as this, any of these oxidizing agents can actually perform this function. It oxidizes it to carboxylic acid. This is an aldehyde, and this is a carboxylic acid. Alright, so that is that. Now, this is furfura. You were taught that when H2SO4 reacts with monosaccharide, it gives a furfura derivative. Can you remember those biochemistry? It's not too fresh in the brain, but I know there's something like that we did in furfura. They say it gives a furfura derivative which reacts with after naphthol to form something. right? You can still remember. I think. Let's come back. So this will give us something like this. We did it in biochemistry, fufura. And it's one of the tests for one of those carbohydrates. We did it in the lab. So this will give us something like this. And this will give us CHO. Now this is what we call fufura. Now, this fufura can react with silver oxide, which is an oxidizing agent in H2O to give furanic acid, right? So the product of this reaction will be something like this. This double bond O. This aldehyde group here, this is an aldehyde, will be oxidized to give us a carboxylic acid, right? So this is the carboxylic acid that will be formed. So from here, you see aldehyde is oxidized to a carboxylic acid. Quite easy, right? Aldehyde is oxidized to a carboxylic acid. Quite easy, right? Very easy. Now let us try for those of ketones. The ketones. Ketones are something like this. The noise here is becoming much. A compound where there are so many children. I don't know. But we'll have to manage because I'll be postponing this for a long time. So this double bond O. And then you have this, right? This gives us CH3COOH. Now, what is the name of this compound? This compound is what we call, or this reagent is what we call parasitic acid, right? Parasitic acid. Now, this parasitic acid, we said, whenever ketones react with parasitic acid, it gives the ester, such a way that this one oxygen, you know, what parasitic acid actually does is to bring in oxygen into the reaction. Then it changes back to its normal carboxylic acid. If you want to take it that way. So this will be H3C. Here will be double bond O. Of course, we say oxygen will be brought into the equation here. So we have CH3 plus acetic acid. Right? So this is, let's say, a ketone reacting with a parasitic acid to give an ester and then the corresponding acid. Parasitic acid will give us acetic acid, right? With an ester. So whenever ketones react with parasitic acid, it gives us the ester and the corresponding acetic and the corresponding acid rather. So we have this. This is cyclic ketone, which we can easily call cyclopentanone. Now, when cyclopentanone reacts with parasitic acid again, which we can take as CH3COOH, the product of this reaction will give us, surprisingly, a lactone. Now, lactone is a cyclic ester. Lactone is what? A cyclic ester. It's a 6-membered ring. You know, this initially was 1, 2, 3, 4, 5. This 5-member ring, right? But this parasitic acid is bringing in oxygen into this ring. That means the carbon adjacent to this oxygen here, or to the carbonyl group. Recall that here it was. So, like I was saying, this group here is the carbonyl group. When we added the oxygen here, we added the oxygen to the carbon adjacent to the carbonyl compound, right? Which is this, or let's say the carbon, we added it in between the carbonyl compound and the other carbon, which is in between here. So in this case now, what we are going to do is, if you add one oxygen to this, it becomes a 6-membered ring. And the 6-membered ring is supposed to give us something like a cyclohexane. So which is something like this as the product here. Cyclohexane, but one of them will be replaced by an oxygen. So we have this double bond here. Of course, we are expecting the oxygen to be somewhere around here since it's close to the carbonyl group, right? So this gives us something like this. Something like this. And then you have double bond O. Now this group here is what we call a lactone. So we can say a lactone is like a cyclic ester. Lactone is like what? A cyclic ester. Cyclic ester. That will be the product of this reaction. Plus, of course, the acetic acid. Because what the acetic acid, parasitic acid does is just to bring in one oxygen so that it will remain its normal form, which is the corresponding acid, which is acetic acid. Now, the next one we are going to look at is, okay, let me clear this and use this slide, is benzoin. So you have something like this, and then you have something like this, pH, and then you have double bond oxygen, and then you have OH, then you have Cu, SO4, pyridine. Now, you know, whenever you have this is an oxidizing agent in pyridine. Now, what does that mean? It means that it is oxidizing specific thing, because pyridine with anything mixed together like this, a mild oxidizing agent, right? So it will oxidize this to give us a ketone. So this is more like a secondary alcohol. This will be oxidized to give us a ketone, and then we'll have this as a product of the reaction. So this will be oxidized, this group here, which is the OH. Now, if I may ask you, this OH here, is this secondary OH or primary? This is secondary. You know why? Because this is a phenyl ring. A phenyl ring is more like something like this attached. But if you want to bring this O compound out the way it is, it's something like this. You have double bond O, and then of course you have this phenyl ring. This lady. And then you have this phenyl ring. This is the structure that you see here, OH. So this carbon here, right? And this group here is another carbon. So you have two carbons attached to the carbocation, the OH. What kind of alcohol automatically becomes this? It becomes a secondary alcohol. Now, these secondary alcohols can be oxidized to give us a ketone, because we say secondary alcohols are always oxidized to give us ketone. So the product of this reaction will be something like this, pH, and then you have double bond oxygen, because you have pH, double bond oxygen, and then this is the product of this reaction, and this is what we call benzyl. Now, when this benzyl reacts with peracid, could be peracetic acid or any of the peracid. Now, it is going to give us a product. Now, what product would that be? Now, when this benzyl is treated with peracid, now we said that whenever a compound, a carbonyl compound like this is treated with peracid, what the peracid does is just to bring in oxygen. So the product of this reaction, when it reacts with the peracid, sorry for this break, I have so much noise here this afternoon. So when it reacts with the peracid, we said whenever parasitic acid or peracid reacts with an aldehyde group, or not aldehyde per se, a carbonyl group, the oxygen acts to like the middle between the carbonyl and the next carbon, right? So this is the perfect position, and we say the product that is usually formed will be an ester. So the group we add here, and then we are going to form something like this as our product. We're going to give oxygen, and then we have the phenyl ring, double bond oxygen. Then we'll have double bond oxygen, and then we'll have the phenyl ring. And this will be the product of the reaction, and then we call this the ester functional group, right? And that will be all for oxidation reaction. I think, yeah, that will be all for oxidation reaction. Now, don't think I forgot this reaction. I actually saw these questions here while I'm still making research on most of them. I actually have the answers to them, but I want us to practice, try as much as possible to get them. Then as time progresses, I'm going to make a lecture on this and this. But know that this one, it will undergo condensation reaction to form this. Then this, now you cannot come here easily to transform this to transform this to this. using what? Using copper sulfate and pyridine, right? We can still remember to convert this to this. This particular one will undergo a condensation reaction. So make your research, and then we are going to look at it together. Thank you very much for your time. Our next lecture will be on reduction reaction.